is incorporated into a theory called the Standard Model, which was essentially finished in the mid-1970s. But now we're stuck. There has been essentially no progress on the frontiers of physics in the last 15 years. We're really paying the price of our past successes. The Standard Model works so well that experiments seem just to again and again verify that the Standard Model is correct. But the Standard Model is clearly not the final answer. The Standard Model has a number of arbitrary features, a number of aspects of it just have to be put in by hand in order to match experiment. And furthermore, it leaves out one of the fundamental forces of nature, the force of gravity. So we're not finished with our task, but so far we don't seem to be able to get any help from experiment in making the next step. In order to break out of this impasse, since the early 1980s, physicists have been making plans for a new experimental facility, a brand new particle accelerator called the Superconducting Super Collider. This is, let's see, I have to, oh yes, this is a cutaway view of the site of the Superconducting Super Collider. I don't have a pointer, so I will have to use, let's see, are there any shadows? No, that doesn't work. This is a bit of Texas. You can see up on the side here Fort Worth and Dallas, and this dashed red line, which runs mostly through this formation called the Austin Chalk, is the Super Collider ring. It's a 54-mile circumference oval with the town of Waxahachie in the middle. The reason for putting the Super Collider in this particular position, aside from Texas politics, is the fact that this formation, the Austin Chalk, which was laid down around 80 million years ago when dinosaurs still walked the hills of western Texas, is marvelous for tunneling, very strong and yet easy to cut through, and also because of this object up here in the upper right called DFW Airport. The Super Collider will be the site for research not just of a team of physicists at the Super Collider, but for physicists who fly in from all over the United States and indeed from all over the world. Within this ring, the magnets will focus and keep on track two slender beams of protons. Protons are elementary particles that form the nucleus of the simplest atom, the atom of hydrogen. They're charged, and they will, electric and magnetic fields will force them round and round faster and faster as they go many millions of times around this 53-mile track. The next slide shows a cross-section of the tunnel within which these two beams will, let's see how to work this. Oh, yes. The next slide shows a cross-section of the tunnel within which the two beams will circulate. It's only about 10 feet wide, 53 miles long. Here are the two beams, one on top, the other below, going in opposite directions. Most of the cost of the Super Collider, $8 billion, goes into these magnets that keep the beams going around along the oval and keep it from plowing into the side of the tunnel, which would be deplorable. At various places, right now it's planned to have 4 of these around the tunnel. There will be special steering magnets which will bring the beams of protons, which remember are going in opposite directions at nearly the speed of light, into collision. And experimentalists will be waiting there, waiting to sort out what happens in these collisions. The next slide shows what happens. Oops, that going the wrong way. No, I'm sorry. Okay. This is a detector this is at one of the 4 stations. This is a typical detector. You can get the scale from the fact that there's a dump truck here and a little man. So this is a large apparatus. This cost of these detectors is comparable to the cost of an entire accelerator laboratory of the previous generation. This is about 50,000 tons of iron, about the same as the battleship Missouri. And the beams are coming along here and brought into a collision. And when the protons collide, all of the energy, since they're colliding head-on, all of the energy is made available for the creation of new forms of matter. And that's what we want to do in this accelerator, to take this energy, it's an energy of 20 trillion volts in each beam, and make it available for the creation of new kinds of particles. That's the energy, when the 2 beams collide, the energy available will be enough energy to produce 40,000 hydrogen atoms. Of course, that's not what we're trying to do. We're trying to create entirely new kinds of matter, particles that are so heavy that we haven't had enough energy to produce them in any laboratory up till now. Here is a somewhat fanciful view of what one of these collisions, whoops, I have to go back. Sorry, these slides got out of order. This is a somewhat fanciful view of what one of these collisions looks like. The beams come together and the particles, large numbers of particles are created, and they're in a magnetic field which makes them curve because charged particles moving rapidly follow curved paths in a magnetic field. And from the curvature, physicists studying these pictures will be able to deduce the momentum of the particles and the energy of the particles, and then you'll be able to figure out the mass of the particles and find out what kind of particles they are. This is a kind of typical event, and is probably, just looking at it casually, a junk event. Junk events are those which don't reveal anything new. When the 2 protons collide, it's a little bit like 2 garbage trucks colliding and just becomes a mess. Nothing very interesting happens. About 100 million of these events happen a second when the super collider would be, or will happen a second when the super collider operates. It is impossible to study that many events, and so computers will take a fast look at each event and decide whether anything interesting has happened, and if nothing interesting has happened, they will just discard the information. And perhaps, if we're lucky, 1 out of 100 million events will be interesting, and the computers will store that information. Now, work has begun on the super collider. As you see here, this is a picture of the digging going on right now. This is one of the experimental holes 200 feet below the surface of Texas. If you look down, if you look up here, there's a shaft that goes up to the sunlight, and that's what is used to lower apparatus down into the tunnel. And then if you look down this way, there are, you see the tunnel going off into the chalk, and there are 2 men there looking up. I don't know what they're doing. Can we have the lights back, please? The super collider is planned to cost about $8 billion, so it's not surprising that there's a certain amount of opposition to the super collider. It comes not only from frugal congressmen, but also from scientists who would rather see that money spent in their own fields. There's a lot of talk about big science versus small science, and the super collider is often cited as a classic example of what's wrong with big science. Very often this is done linking the super collider together with the space station, which I find absolutely infuriating, because the space station isn't big science or small science. It's not science at all. I am not a big scientist. I have a small research grant from the National Science Foundation supporting 3 or 4 theoretical physicists, and we work with pencil and paper. But we can't do our work without the data that will be provided by the super collider. However, I'm not here to sell the super collider to you. In the last decade, however, I've had to give a lot of public talks and also congressional testimony trying to sell the idea of building the super collider. And I find again and again in doing this that the most important thing I have to explain, and also the most difficult thing to explain, is the pattern, is our peculiar view of the pattern of scientific knowledge which motivates building the super collider. And it is that pattern of scientific knowledge, what it is that we are trying to accomplish, what is the historical mission of elementary particle physics that I wanted to explain. And that's why I've written this book, which has the same title as this talk, Dreams of a Final Theory, and that's why I'm here talking to you tonight. To start out, suppose you want to explain anything in nature. Suppose some child asks you, why is the sky blue? Or why do stars shine? Or why is the chlorophyll in grass green? Well, child might not put it that way, but now, if you know a little bit about these things, you could probably answer those questions in terms of a number of separate sciences. There's a science of chemistry, there's a science of optics, and so on. And then if your interrogator, an unpleasant little child, asks you, well, why is that true? Why are these rules of chemistry what they are? Why are the rules of optics what they are? Well, we've known how to answer those questions since the 1920s. We have answers in terms of the quantum mechanics that describe the particles, electrons, atomic nuclei, and photons that make up ordinary matter and radiation. And then suppose you were asked, well, why is that true? Why is it that the electrons and the nuclei and the photons, by the way, are just the particles of light, why are those particles what they are? Why do they have the properties they have? Well, we could answer that too in terms of what earlier I called the standard model of elementary particles. We've had this in hand since the mid-1970s. It's a theory of fields. Just as the photon, the particle of light, is actually a little bundle of the energy and momentum that's carried by electric and magnetic fields, all the other particles, electrons, for example, are bundles of energy in different fields. There's an electron field. There isn't any field for an atomic nucleus or for the protons and neutrons that go into an atomic nucleus, but there are fields for other particles called quarks, out of which the protons and neutrons are made. We have a field theory of all these particles, which explains also the forces among them, and it works. In other words, we have a convergence of scientific explanation. You can think of the space of all possible scientific principles as being filled with arrows. Think of each scientific principle as being connected by arrows to the principles by which it's explained. If you trace these arrows backward, they all seem to converge into a common source. Leaving out things having to do with gravity, they all converge to the single common source of the standard model of elementary particles. Wherever you start, whether you ask about why the sky is blue or you ask about why the stars shine, you always get the answer in terms of the same simple underlying theory. And now we want to make the next step. The standard model is certainly not the final answer. It doesn't include gravity. It has a lot of arbitrary features. But that's what I mean by a final theory. What I mean by a final theory is the point of convergence, which we haven't yet reached, of all of these arrows of explanation. Well, that's what I mean. There are many other things that I don't mean and that sometimes get confused with the idea of a final theory and are pretty silly. First of all, I certainly don't mean that a final theory will end science. Even now, we believe that, for example, the DNA in your genes that makes genetics work the way it does, DNA is a very large molecule containing millions of atoms. We believe that DNA works the way it does because of the ordinary rules of quantum mechanics applied to electrons and atomic nuclei. But no one can use the rules of quantum mechanics to actually calculate the properties of the DNA molecule. Just too complicated. So knowing the underlying theory, which in this case is just quantum mechanics, doesn't help us understand genetics very much, doesn't help us to understand DNA. In the same way, finding the final theory is not going to help us very much understanding DNA or life or even things in physics itself, like turbulence. There'll be still lots of scientific problems left to work on. A final theory will be final in only one sense. It will end the search for those principles that have no explanation in terms of deeper principles. Another qualification is that we're limited in what we can explain, not only because things are complicated, the way the DNA molecule is complicated, but also because other things intrude, in particular the element of history. When you're talking about sciences like biology or astronomy or geology, you need more than just the rules that govern the objects that these sciences deal with. You also need the initial conditions. You need something about the history of life on Earth or the Earth itself or the whole universe. Right now, just as it was in Newton's day, there is a split in scientific knowledge. On one hand, we have rules, laws of nature, whether they're Newton's laws or Einstein's laws or the Standard Model, which tell you what will happen if you put together a certain amount of matter and energy and bang particles together. Whatever you want to do, it will tell you what will happen. Then there are initial conditions, which tells you how the universe actually started, what is actually happening now. Right now in physics, as it has been ever since Newton, we have an absolute discontinuity between the rules, the laws of nature, and the history, what is actually going on. The laws of nature leave open the possibility there's no universe at all. But we know there is, and the fact that there is a separate fact which isn't explained by the laws of nature. That may not be permanently true. Stephen Hawking, who was here a year ago, together with James Hartle, have discussed a very interesting idea of how the laws of nature, when properly interpreted, and he's thinking particularly of quantum mechanics applied to general relativity, will show us that there really is only one possible kind of universe we could have. It's really premature to say whether this attempt is going to work or not. It's very controversial, and right now I think physicists are quite undecided. They simply don't have enough information to decide whether or not history and physics will eventually fuse into one science. So we have to leave that as an open question for the future. But even if Hawking is correct, and even if eventually we will understand the initial conditions of the universe in terms of the law of nature, as a practical matter, we will always have to deal with nature, with the history of the universe as a matter of accidents. We will never be able to explain in detail why it rained today, yesterday, but not today. We know the rules that govern the weather, but it's just too complicated. It will always seem to us as somewhat of an accident how the stock market works or why the weather works the way it does, and so on. There's another deeper reason that there's another deeper factor that limits us in using the laws of nature to explain everything we see, and that is that many of the things we are interested in really don't have to do with what's going on at the ultramicroscopic level. For example, suppose you could follow the motion of every atom in a fruit fly or a mountain brook, and you had a computer that could predict what would happen at every moment in the history of that object. And you would get a mountain of computer printout, as large as Mount Hood. And what would you do with it? Looking at that mountain of computer printout, you still wouldn't know whether the brook was turbulent or the fly was alive. These are questions that have to deal with nature on a level of complexity much greater than the level of the individual particles, but it doesn't change the fact that the DNA in the fruit fly and the turbulent eddies in the mountain brook work the way they do because of the rules of quantum mechanics, and that works the way it does because of the Standard Model and so on, ultimately traceable down to a final theory. Now, in this search for a final theory, we, of course, need experimental observation. We need apparatus like the supercollider. Oddly enough, though, one of our chief assets is perhaps often more important than scientific apparatus, is something you don't normally think of in connection with science, and that is our sense of beauty. And this is important to us not only in conceiving of new theories, which is an act of inspiration that might be compared to artistic creation, where you might think a sense of beauty would be useful, but even in judging the validity of theories that are presented to you, say, in a scientific paper. And that seems very odd, but it's historically the case that very often physicists and other scientists have been better served by their sense of beauty than by experimental data in judging which theories are correct and which theories are not. For example, when Einstein first developed the special theory of relativity, almost immediately in Berlin, experiments were done by a man named Kaufmann, which showed that experiments that measured the way that very rapidly moving electrons would bend in a magnetic field. These experiments showed that Einstein's theory was wrong, and that another competing, much uglier theory, due to a man named Abraham, was correct. Einstein amiably ignored this experimental data. Abraham's theory was just too ugly to take seriously. Einstein, of course, was right. And in my own work, I've seen this again. The unification of forces that was my contribution to the Standard Model was challenged in 1976 by experiments done by very competent experimentalists both at Oxford and Seattle. And for several years, we were very worried about it. And then one experiment was done in Stanford which verified the theory, and immediately everyone in the world of physics concluded that the theory was right after all, although the score was 2-1 against it. The reason was that during those 2 years, from 1976 to 1978, we had tried very hard to find alternatives to the Standard Model, and all the alternatives we were able to think of were horribly ugly. And we felt better one experiment which verifies a beautiful theory than 2 experiments which force us to an ugly theory. This may sound irresponsible, but in fact, a theoretical physicist who did not rely on his or her sense of beauty in judging experimental data as well as mathematical ideas would not be in a good position to make progress. Now, this is really very odd. What is there about the sense of beauty of a human being, a physicist, that should be of use in deciding which theories are correct or not? I mean, isn't experiment supposed to be the only thing we go by? How come this works? There's something spooky about it. I can offer a number of suggestions on why the sense of beauty is so valuable to us. Some of them apply to science in general, but some of them apply, one of them, the last one, applies very specifically only to elementary particle physics. The first suggestion is that the universe has been operating on us as a rather random, inefficient, but in the long term very effective teaching machine. You know, through natural selection, atoms of carbon and hydrogen and oxygen and nitrogen came together to form amino acids in the earth early, and they formed proteins, and eventually out of this mess came bacteria and protozoa and fishes and ultimately people, through a process of natural selection. Those life forms that weren't able to reproduce themselves simply got lost, and the successful ones are the ones that propagated to the present. In the same way, we've had a natural selection of ideas. We've gotten it beaten into us by nature that things are a certain way, and that we've come to think of that way as being a beautiful way. Another reason I think in general in science that the sense of beauty is so helpful to us is simply because we choose problems because we think they're likely to have a beautiful solution. And you see this very often in physics, that the effort goes into the problem that is expected to be solvable in beautiful terms and not into the others. For example, a very common phenomenon that most people are aware of is the fact that when iron cools below a certain temperature, 770 degrees centigrade, it becomes spontaneously magnetized. Now, that's been studied by physicists for a long time. Most of the effort in the last 3 or 4 decades has gone into studying the way that the magnetization vanishes when the temperature of the iron is raised to that critical temperature, 770 degrees. Because at that temperature, the magnetization of any permanent magnet is wiped out. Physicists have studied in great detail in fact, some of the leading theoretical physicists in the world have given large parts of their career to studying the way that the magnetization of a piece of iron vanishes as the temperature rises to 770 degrees. Very little attention has been given to calculating that temperature, 770 degrees, and explaining why it's that temperature and not some other temperature. The reason is that the first question, how the magnetization vanishes, has a very beautiful solution. And really is one of the prettiest things in the whole study of condensed matter. Whereas the other question, what is the temperature at which the magnetization vanishes, has an ugly solution in terms of the details of the materials, an ugly solution which really cannot be expressed in any simple, elegant way, and has to be done separately for each kind of magnetic material. So it's not surprising that the physicists found a beautiful solution to a problem they chose because they thought it would have a beautiful solution. Well, so much could be said for science in general, but there's another reason for the success of our idea of beauty, which is more specific to elementary particle physics. Sometimes in conversations among theoretical physicists dealing with elementary particles, it seems that mathematical ideas are incredibly potent. Something about our theories is working much better than it should. We have the feeling that there's something behind the blackboard that makes our theories work so well. And I think what it is that we're getting a premonition of the beauty that we will find, perhaps not too far in the future, in a final theory. The particle physicists can really say with John Donne that if ever any beauty I did see, which I desired and got, 'twas but a dream of thee. I don't know who John Donne meant by thee, but for us it's the final theory we're dreaming of. Now, what is the nature of the beauty that we find and that we hope to find, especially in a final theory? It's not exactly the same as the beauty you find in most works of art. It's more like the beauty of a sonnet, a Shakespearean sonnet, than one of Shakespeare's tragedies or comedies. It's a beauty that comes from rigidity, from the feeling that there's nothing you could change without spoiling the theory or the sonnet. That isn't true of artworks in general. I mean, in fact, theatrical directors, when they put on plays of Shakespeare, usually leave some things out just because the plays are too long. And the performances work. You know, when Olivier performs Hamlet in the film, he never says, "Oh, what a rogue and peasant slave am I." A famous speech, but he leaves it out. And yet the performance works perfectly well because Shakespeare's Hamlet is not a perfect jewel of a work. It's a large, passionate work whose passion and complication and messiness mirrors something about human life and the human soul. Whereas in the Shakespearean sonnet, you wouldn't want to leave out a line. You wouldn't want to leave out a word. The beauty of physical theories is more like the beauty of the sonnet than Hamlet. One particular form of beauty that seems to be present in all our theories and gives them a good deal of the rigidity that they have, the unchangeability, the uniqueness, is principles of symmetry. Now, a principle of symmetry is simply a statement that something looks the same from several various different points of view. For example, the human face is perfectly symmetrical not perfectly, but to a good approximation, symmetrical between left and right. And as a result, we can be pretty sure that when this young lady looks in the mirror, she will see the same face that we see just looking at her directly on the slide. The human face is symmetrical between left and right, and therefore its appearance does not change when you view it in a mirror. That isn't true, for example, of flounders. Now, there's many symmetries like this. A cube or a sphere obviously has more degrees of symmetry than the simple left-right symmetry of a human face. And artists and scientists have been interested in symmetry for thousands of years. But these are the symmetries of things, and they are not really the most interesting kinds of symmetry. After all, it certainly is not true that the most interesting thing about her face is its symmetry between left and right. The symmetries that are really important to us in science are not the symmetries of things, like the human face, but the symmetries of laws. A symmetry of a law of nature is a statement that when we view the world from different points of view, we see the same laws. For example, there is a symmetry of the laws of nature called rotational invariance that says that we discover the same laws of nature however our laboratory is oriented. It doesn't matter what you call north or east or up. The laws of nature do not vary with the orientation of the laboratory. That's a relatively new discovery. It was certainly not true in Aristotle's physics. Aristotle's physics assumed an absolute distinction between up and down. In fact, it's really very sophisticated of us to get beyond the everyday experience of up being different from down and seeing that they really just seem to be different because in one direction there's a large mass, the Earth, and in the other direction there's just empty space. But the laws of nature don't have written into them a distinction between up and down. Now, that's, of course, a symmetry which applies to the laws of elementary particle physics as well. But elementary particle physics, the standard model, is governed by other, more esoteric symmetries. There are changes of point of view, not just about the orientation of the laboratory in space, but about the types of particles that we have. There is a symmetry that says that we can, everywhere in our equations, we can interchange where it says electron with another particle, the neutrino, and replace all the electron symbols in our equations by neutrino symbols, and vice versa, and the equations are the same. So the equations do not make any distinction between these two types of particles, electrons and neutrinos. By the way, I'm assuming everyone's heard of electrons. Neutrinos are particles which are rather like electrons, except that they have no mass or very little mass and no electric charge, whereas electrons, of course, have mass and electric charge. But they have very similar interactions, and they spin in the same way. There are other particles that similarly have to be interchanged at the same time. The laws of nature are not unchanged if we just interchange electrons and neutrinos and do nothing else. We also, at the same time in our equations, have to interchange the photon, the particle of light, with other particles that are less familiar called W and Z particles, which carry certain forces that are responsible for the main types of radioactivity. And this symmetry then imposes a unification between the electromagnetic forces which are produced by the exchange of photons and the forces responsible for radioactivity called weak nuclear forces, which are produced by the exchange of W's and Z particles. These symmetries are hidden from us. And I don't think I have time to explain that, but I'll respond to questions about that, which was why it was hard to find them. But this really is a major part of the discovery of the Standard Model, to realize that these symmetries are there, although just as in the case of Aristotle, not realizing the symmetry between up and down, it was hard for us to see them in nature. Another source of rigidity in our understanding of nature, by rigidity I mean that you can't change anything in the equations without the whole thing collapsing into a logical absurdity. Another source of rigidity is the fact that we discover infinities in our calculation. That is, we set out to do a perfectly simple, straightforward thing like calculate the energy of an electron in a hydrogen atom, and when we calculate to a certain approximation, we get a perfectly good answer which agrees with experiment to that accuracy. And then when we try to improve the approximation, we get an answer that the energy is infinite. That's nonsense, and it clearly shows something's wrong. We've learned how to solve this problem. We've learned how to deal with these infinities. But in fact, our way of grappling with them and getting rid of them in our theories only works in very limited classes of theories. And that's really wonderful, because it means that in order to avoid the logical absurdity of infinite quantities, when you ask perfectly sensible questions, we may be led to just one theory. Only one theory is logically consistent. It doesn't give you infinite answers. In particular, the problem of infinities is particularly severe when we apply it to quantum mechanics, to gravitation. And in recent years, there has developed a new kind of physical theory called superstring theories, which probably are the only way of eliminating the problem of infinities when you deal with gravitation. And therefore, we think superstring theories may be a large part of any possible final theory. Superstring theories, which basically say that matter is not composed of particles at all, it's composed of, particles are just points. It's composed of little lines, little strings, either open or closed, that go zipping around like rubber bands. This theory apparently is the only way of dealing with gravitation on the quantum level, and probably is a large part of the final theory. Now, we can go very wrong in using our sense of beauty. It's not an infallible guide. A famous example of the sense of beauty going wrong was work of Kepler at the birth of modern science. You know, there's a beautiful result of Greek mathematics that Kepler knew, perhaps many of you know, that has to do with regular solids. A regular solid is just any solid object with plane boundaries for which every vertex and every line and every face is just like every other vertex or line or face. For example, a cube is a regular solid. Every vertex looks just like every other vertex. Every line looks like every other line. The Greeks were able to prove, amazingly, that there are just 5 regular solids. There's the cube, there's the triangular pyramid, there's the octahedron, which is 2 triangular pyramids stuck base to base, and then there are 2 others called the dodecahedron and the icosahedron, but just 5. Kepler, as a young man in the early 1600s, tried to make a theory of the planetary orbits based on this fact, this beautiful fact of Greek mathematics. And he assumed that the planetary orbits were in one-to-one correspondence with the, he knew of 5 planets at that time, aside from the Earth, and he assumed the planets were in one-to-one correspondence with the 5 regular solids, and that the orbits were just proportional to the size of these solids when you nested them together in a certain order. Now, that's wrong. I mean, that has nothing to do with the way the world is. it's not just wrong, and when we think about it, we think almost feel a sense of repugnance, and not just because it's experimentally wrong, which it is, because it just seems to be the wrong way to think about planets. But why is it the wrong way to think about planets? It's not the wrong way to think about elementary particles. Some of our theories of elementary particles are really not that different. We don't put the elementary particles into one-to-one correspondence with the 5 regular solids of Greek mathematics, but we do similar games of making beautiful theories. We put them into one-to-one correspondence with other lists of mathematical objects, things called Lie groups. Why do we do that? Why does it work with particles and not with planets? I think it's because particles are important in a way that planets are not important. That was Kepler's mistake. He thought planets were important. Of course, planets are important in some respects, but they're not important in the sense that they're not written into the laws of nature in any fundamental way. The orbits of the planets are historical accidents, whereas the elementary particles, or perhaps the superstrings that underlie the elementary particles, are important. They are what are written into the book of rules at the most fundamental level. And we can see this from the fact that planets are complicated and particles are simple. You know, 2 planets, Mars and Venus, for example, differ from each other in a vast number of ways. Their size, their shape, their color, their speed of rotation, their atmospheres. You'd have to fill many volumes to describe all the ways that Mars and Venus differ from each other. Whereas any 2 electrons anywhere in the universe differ in only their speed, their direction of spin, and that's it. In every other respect, any 2 electrons are identical to each other. In a sense, because electrons are all the same, if you've seen one, you've seen them all, they're really very boring. But that's what's interesting about them. They're so simple that they must be close to a very fundamental level of nature. We're not going to get the final answer just from pure aesthetics or from pure logic. It's pretty clear that there are many logically possible sets of laws of nature which don't correspond to reality. It is possible, however, that the final theory will be recognized as having a kind of uniqueness in the sense of being perfectly rigid, that is, being a theory which cannot be changed in any way, not by varying a constant, not by changing one little rule a little bit, cannot be changed in any small way without leading to logical absurdity. We're not there yet. We don't have a final theory. I hope the super collider will take us there. It may not be the last step on the path. I think it is a step that we need to take. Maybe we'll never get there. Maybe we're not smart enough as a species or rich enough as a society to do what we need to do to find the final theory. So I can't promise you a final theory around the corner. But I do strongly object to those who think the idea of a final theory is absurd, because we never have found a final theory yet, because every theory up till now has always been explained in terms of a deeper theory. That seems to me exactly like, if you can imagine a group of explorers sitting in the Travelers Club in the late 19th century and over their port saying, you know, no matter how far north we go, we always find there's more sea and ice even further north. It's clear we'll never get to the North Pole. Well, people did get to the North Pole. And we too may get to a final theory, and perhaps sooner rather than later. Now, although we don't have a final theory yet, in closing, it's irresistible to ask what effect it will have on the human spirit. What will it mean to us, apart from the scientific details, that we have a final theory? Why is this important to other people than just particle physicists, if it is? Well, we used to believe, as the Psalm says, that the heavens declare the glory of God, and the firmament showeth his handiwork. Well, we don't really think anymore that there's anything special about the heavens that declare the glory of God. We know what the stars are. They're spheres of glowing gas. We know that the the light comes from energy which bubbles up from the center produced by nuclear reactions. It's not stars, not the heavens that are going to declare the glory of God. If anything would, it would have to be the final laws. Having the final laws, we would have the book of rules that describe everything, not only stars and stones, but everything in the universe. It is not surprising that 3 recent books, including Stephen Hawking's, have used the metaphor of talking about the final laws of nature as the mind of God. And Einstein also used this language when he said that he described the aim of the enterprise of physics as not only to know how nature is and how far her transactions are carried through, but also to reach as far as possible the utopian and seemingly arrogant aim of knowing why nature is thus and not otherwise. Thereby one experiences, so to speak, that God himself could not have arranged these connections in any other way than that which factually exists. Well, Einstein's religion was actually very vague, and he probably meant this very metaphorically, as shown by his use of the word so to speak. But it is irresistible for us to use this metaphor of the mind of God when we talk about the final laws. The theologian Paul Tillich observed that among scientists, only physicists seem really comfortable in using the word God in connection with their work, and this is doubtless because physics is more fundamental. The last part of that was my remark. However, my own feeling is that we should resist this metaphor. The word God, of course, is like any other word, is flexible. It can be taken to mean anything you like, and that's what makes it difficult to discuss this, because the meaning of the word tends to change even as you talk. But it seems to me that if words are to have any use to us, we ought to respect their historical meanings and use them the way that they've been used historically, and particularly protect the distinctions between one word and other words which don't necessarily mean the same thing. If someone says God is our better nature, or God is the universe, or God is love, or God is energy, well, you know, then of course you can look for God in different places depending on which you mean. But that seems not to me so much as a wrong view as an uninteresting view, because it makes the word just synonymous with something else. It seems to me that if it's going to be a useful word for us, it should be taken to mean something like what it has meant historically, that is an interested God who concerns himself with human actions, and a God who has not only created the universe but established standards of good and evil. In other words, a God that it's appropriate to worship. The other conceptions of God, are, as I say, are not wrong, because you can use a word to mean anything you like, but they do make the concept less interesting, less important. So for me, the question is, will we find an interested God in the laws of nature? And I think we will not. In fact, I think all our experience throughout the history of science has tended in exactly the opposite direction. It once was true that mankind found no other explanation for natural phenomena. In every brook there had to be a nymph. In every tree there had to be a dryad. Well, we've learned a lot. We still can't explain everything, but we think we know the principles that govern everything. And if not quite, we think we're on the road to knowing them. And as far as we've been able to understand these principles, they're completely cold and impersonal and offer no hint whatever of anything like a divine plan. We do find beauty in the laws of nature, perhaps a beauty that we're trained to find in it, but we don't find any special status for human life or intelligence. We don't find any standards of good or evil. We don't find any God that cares about these things. Still, I think the discovery of the final laws of nature will have a profound effect on human culture. Today, as always in the past, humans are plagued by all sorts of irrationalities. ranging from relatively harmless irrationalities like astrology or creationism to ideologies of the most vicious kind. I think it's easier for people to hope that these irrationalities will eventually turn out to be substantiated because now the laws of nature are still obscure. We still don't know the final answer from the scientist's point of view of why things are the way they are. Finding that final answer, finding the final laws of nature, won't solve the problem of man's irrationalities, but I think it will leave less room for them. And this indeed has happened before. Newton's theory was important to human culture, not because everyone in the 18th century learned calculus and learned how to calculate planetary orbits, but because of the accomplishment of Newton, people began to realize that the heavens were not something beyond human understanding, but the planets were just bodies cranking around in their orbits, governed by mathematical laws, the same laws that govern the fall of an apple here on Earth. And indeed, the historian Trevor Roper has said that it was the diffusion of this message from the success of Newton's theory that eventually put an end to the burning of witches in Europe and America. Well, right now, especially in Asia and Africa, there are dark forces of religious enthusiasm that are gathering strength. And we may again have to look to science for aid in combating them. And this aid will come not because science provides certain knowledge, but just precisely for the opposite reason, because of the uncertainty of scientific knowledge. Seeing scientists change their minds again and again, as we have had to, about matters which are directly studyable in the laboratory and amenable to mathematical analysis, I think makes it very difficult to take seriously the claims of spiritual authority or sacred writings to certainty about things that are beyond human experience. Still, when we know the final laws of nature, whatever salubrious effects that will have, I think we will feel some sense of regret. And here we can find an analogy with the history of geographical exploration. Originally, the main forum in which the search of knowledge took was the exploration of the earth. And when Tennyson wanted to describe Ulysses following knowledge like a sinking star beyond the utmost bounds of human thought, he had Ulysses and his men set sail through the Straits of Gibraltar out into the Atlantic beyond the sunset and the baths of all the western stars. Originally, the map of the earth was largely supposititious, unknown, and the imagination of men and women could fill it with dragons and griffins and anthropophagi. And today, the Earth's surface is mapped. There isn't any more mystery about it. We know every square inch of at least the land surface of the Earth. And the dragons and the griffins are all gone. In the same way, I think that future scientists, knowing the final laws of nature, may feel some envy of us today because we're still on our voyage to discover the final laws. Thank you very much. Yeah, I'm happy to take questions. Everything I said was so uncontroversial that I'm probably isn't any need for any, but there's a gentleman over there.
A
Yes,
large
sir.
part of the standard model has the rigidity that you talk about, the gauge sector. But the part that we're going to be looking at the super collider is the Higgs, or the scalar sector of the particle physics. And there we have naturalness problems, fine-tuning, and we're far away from having even an idea of how we're going to get the clue that turns the standard model closer to the final theory.
Yes, I don't disagree at all with what you say. In fact, I was trying to just hint at that, at what you say, by saying the standard model has arbitrary features. It's certainly not a final answer. In fact, as the gentleman said, the particular features of the standard model that we don't understand and seem most arbitrary are those features that have to do with how the symmetries that underlie the standard model got hidden from view. We have various ideas about how this might have happened. It happened as the universe expanded and cooled. We can fairly well identify the moment in the history of the universe when this happened, but we don't know the details of the mechanism by which it happened. The super collider is designed to solve that problem. And that is why we're building an accelerator that will collide particles together with an energy of 20 trillion volts rather than 10 or 30, because it's been calculated that that's the energy that you need to create the new kinds of matter that will then reveal the answer to this question. This is a question that I've been worrying about myself for 20 years, and I couldn't agree more that there are problems here of finding something that's aesthetically compelling. My own feeling right now is that we will find a beautiful solution to these problems in terms of superstring theory, but so far that's just a hope. I don't know whether you would agree with that. But perhaps another question.
The whole business about...
I think I better take another question from another person.
I am a different person.
Oh, I'm sorry. Forgive me.
At least
You say it's much like electrons. Forgive me. Your voice sounded just like the previous guy, and I can't see you.
The business about symmetry and throwing out different laboratory experiments that discount your theory to one that's more simple sounds like bad science to me, going up through school being taught that any theory that comes up with an experiment that makes it untrue is thrown out for a new one. I don't understand it.
Yeah, okay. Well, I think I was being a little flippant in the way I described it. Your question is perfectly fair. Certainly, in the end, experiment decides. And we can have the most beautiful theory in the world, and if it's consistently and repeatedly contradicted by experiment, eventually we have to abandon it. Oddly enough, that doesn't happen. When we have really beautiful theories that have some experimental support and some experimental contradiction, the experiments that contradict it usually go away. Experiments are difficult. And it is, remember, the experimentalist is always faced with a real-world situation where he or she is measuring something, but there's all kinds of other things going on that are irrelevant to what's being studied that have to be regarded as a kind of noise and that have to be subtracted off or taken account of in some way. And the experimentalist always has to do this as well as he or she can. Sometimes they just don't succeed. And we've seen this happen again and again. The standard model, since its inception, since its completion in the early 70s, has been challenged by a series of experimental discoveries, each one of which showed it was wrong. And in each case, the experimental data was found to be wrong. Well, there's nothing so surprising about that. Experimentalists are human beings like anyone else. Of course, if those experiments had gone on year after year, continually showing the same thing contradictory to the standard model, we would have had to give up the standard model. But one experiment never proves anything because the experiment could be wrong. And if it contradicts the standard model, it is wrong.
Okay.
Yeah. I have some questions on cards, and then I'll be glad to come back to you. How do you regard the argument that the apparent fine-tuning of the fundamental constants is evidence that the universe is the design of a purposeful creator? Well, this is an argument that's often been made. This is an old question. It is true that if you start varying the constants of nature too much, you'll get to a universe in which you can't imagine how life could have evolved. I don't think the evidence is very strong that the constants have been precisely fine-tuned. It seems to me that you could vary most of the constants of nature by quite a lot, and not necessarily rule out the possibility of intelligent life. Of course, it wouldn't look like us, but you don't necessarily lose all of evolution and the possibility of intelligence appearing just by changing the fine structure constant by 10%. So I'm not that impressed with the fine-tuning. I have yet to be shown any really striking example where the fine-tuning works. Even if it does, however, prove that there is fine-tuning, and with regard to one constant of nature, known as the cosmological constant, I think there the evidence is somewhat convincing that there is a certain amount of fine-tuning. I don't think that necessarily proves anything about the universe being the design of a purposeful creator, because there is an alternative way of looking at it. Modern cosmological theories, especially those that arise when you apply quantum mechanics to the whole universe, suggest that there isn't just one universe, but that there is a wave function which contains, among the many possibilities it describes, many, many different things that we would call universes. In other words, what we call the universe is just part of a mega-universe. And that these universes may, in fact, and this has come out of the work particularly of Sidney Coleman at Harvard, these universes may, in fact, differ from each other precisely in the values of the different, what we call fundamental constants. In most of them, the constants presumably take values which are hostile to the appearance of life. Naturally, in any world in which there are people like we're here discussing the universe, that they have to be living in a universe where the constants take values that are favorable to the appearance of life. So it's not surprising that we find that the constants have those values. What else would you expect? In other words, it's like people who didn't know anything about astronomy wondering why the heat that comes into the Earth from outer space, suppose they don't know about the existence of the sun, has a certain value, 2 calories per second per square, 2 calories per second per square centimeter. Why that value and not 1,000 or 0.0001? Well, they could actually think, well, you know, if it was much less than 2 calories, it would be too cold for life, and it was much more than 2 calories, it would be much too hot for life. Therefore, this constant has been fine-tuned to make the Earth habitable to life. Well, that's not true at all. In fact, we're on the Earth because that's where people can live. And there are other planets like Pluto where the constant is very small, and other planets like Mercury where it's very high. And we're not there because we couldn't live there. So and that has nothing to do with divine plans. You had a question?
The most amazing thing about physics has always been, to me, why the universe is so uniform, both at the close to the subatomic scale and on up into the macroscopic scale. Why are the constants the same over there as they are over here? What connects things? Or is it all history? Or are there some ways of exchanging things so it levels out?
Well, we know it's uniform within the 10 billion light years or so that we can see. And it may not be uniform beyond that.
But at the local level, why does it have to be?
What?
At the local level, why does it have to be? Besides, of course, that's the only thing we could see.
Well, we have built into the laws of nature, as we understand them, symmetry principles that say the rules have to be uniform. The laws of nature appear the same whether you're here or in the Andromeda Nebula or in 3C295. Whatever it is, the laws of nature appear the same. Now, this is a symmetry of the laws of nature. These symmetries are among the most fundamental things we know about nature, and until recently it wasn't possible to ask why they're true. They're so fundamental that we explain everything else in terms of them. In superstring theories, we can actually explain symmetries like this, or we hope we will be able to explain, as just the properties of the solutions of the equations of the superstring theory. We're not at that point yet, but we can begin to see how that might be. That's the uniformity of the laws. Then there's the question of the uniformity of what we actually see, the population of the universe, the fact that there are about as many galaxies per cubic million light years around the Earth as there are very far away. Well, that has to do with the initial conditions of the universe, and right now that's disconnected with the question of the laws of nature, although, as I suggested earlier, maybe eventually it will be tied up with them. I have another question here. How do you, let's see, a final theory is not absurd. However, by now a final theory will be so far removed from any interesting question of science, even physics, that it will be boring. Comment. Well, it depends on what turns you on. If your idea of interesting is that it will explain things that you need to know for industrial or medical purposes, then you may be right, although it's premature to say that. The development of quantum mechanics in the 1920s seemed very esoteric, but in fact it had an enormous effect, and a large part of the gross national product now comes out of industries in which you have to know quantum mechanics in order to, say, design a transistor or work out the properties of a new chemical. We don't know whether or not knowing the laws of nature will help us to do things industrially or medically. But suppose they didn't. Let me grant you that they never will, just for the purpose of argument. Suppose knowing the final laws of nature is of no use in understanding properties of transistors or fluids or chemicals or medicines or whatever. I still think it's interesting because I want to know why the world is the way it is. I understand why transistors work the way they do in terms of a theory of solids based on the quantum mechanics of electrons and photons. And I know why that works the way it does in terms of a deeper theory. And I know why that works the way it does in terms of a deeper theory, but now I want to make the next step. I can't help find this interesting. I want to trace these questions of why the world is the way it is down to their roots. Now, if you don't find it interesting, too bad. If I can make an analogy, the Nile has been interesting for many thousands of years. The Nile is Egypt is called the gift of the Nile. There wouldn't be any Egypt without the Nile. The discovery of the source of the Nile was of no value in helping the problems of Egyptian agriculture. But who could say it wasn't interesting? Another question?
I'd like to know how you personally like to solve Bell's theorem of non-local events.
Well, the way I solve it is just to say that's the way quantum mechanics is, and it doesn't bother me anymore. Bell's theorem, Bell studied an experimental setup that had originally been suggested by Einstein, Podolsky, and Rosen in the 1933 Solvay conference. Einstein was hostile to quantum mechanics, and he was trying to show how absurd the conclusions of quantum mechanics were. And he showed that, according to the interpretation of quantum mechanics, measuring something in one laboratory would change the wave function of the universe instantaneously all over the universe. And John Bell of England and Geneva really elaborated on this and found a way of really testing any alternatives to quantum mechanics. And it turned out when these experiments suggested by Bell were done, that quantum mechanics is right. Well, that's the way the world is. The world is not something that obeys common sense rules. It obeys the rules of quantum mechanics. It doesn't bother me. I don't know why it bothers everyone else. Quantum mechanics works, and I have no trouble with it. Oh, I'm sorry. There are people over there. I can't see you. In fact, it's completely hidden, but thank you.
I have a question about your use of aesthetic principles in terms of deciding which theoretical models to follow and which to reject, or which might be more interesting or enlightening. In that, I assume that you support the teaching of science and mathematics. I would also assume that you would support the teaching of aesthetics. And do you have a principle or a theory or a science of aesthetics that you operate from in order to make these choices?
No. And in fact, insofar as I have a science of aesthetics, you've heard it. No, and I'm dubious about the value of it. I think science doing science is a little bit like riding a bicycle. It isn't really helpful to get lectures on how to ride a bicycle. You do it, and you get used to doing it, and then it becomes natural to you. I can't imagine really lectures about or formalizing the aesthetics of science in a way that would actually be useful to scientists. In fact, there's a whole chapter in the book called Against Philosophy, in which I argue that nothing in the work of the philosophers of science has turned out to be of any value to scientists. And I would say the same would be true about an aesthetics of science. I'm not sure that the philosophy of aesthetics is of any value to artists either, for that matter. Gee, a lot of questions. How will the computers know what an interesting event looks like? Yes, this refers to that. That's a very good question. They will be told in advance, of course, by people. And the people will tell them that, for example, if a particle comes out of the collision at a very large angle, that means it was produced when two quarks, one in each proton, hit each other head on. So that the energy of the collision didn't go into just the production of thousands of protons and neutrons and mesons, but it went into this one new particle. That would be a very interesting event. That's the sort of thing. You look for tracks that come off at large angles to the beam direction, or another thing you look for are events in which there seems to be more energy flowing in one direction than another direction, violating the principle of the conservation of momentum. I mean, since the two protons hit head-on, there's no net momentum. The momentum of the two protons cancel. And therefore, all the momentum of all the final particles has to add up to zero, which means, roughly speaking, there's as much energy flowing in any one direction as any other. And if you find that isn't true, it must be that there are particles you're not seeing that are flowing in the directions where you don't see anything going. Particles like the neutrino. So you will recognize there are events that are producing neutrinos, and these events are interesting because it means some heavy particle was produced that's decaying into neutrinos. But different experiments will define different kinds of events as interesting. And in fact, this is the art now of experimental physics in this area. The art of experimental physics is to decide in advance what kind of thing to tell the computer to look for. Any insight about mass, post-Mach? Oh, forget Mach. Well, this question, I'm glad you asked about mass, though, because the question of how the symmetries in the standard model get broken is also the question of where mass comes from. If these symmetries were, I didn't really explain all this, but if you have a symmetry, it's a certain property of the equations that say the equations look the same if you interchange some things, like you interchange electrons and neutrinos. Now, you might think that if you have equations that say the electrons and neutrinos appear the same, if you have symmetries that say the electron and neutrino appear exactly the same way in the equations, then in the solution of the equations, you should find the electron and the neutrino have the same properties. If the electron has a mass, the neutrino should, vice versa. Well, that's not true. If you think about it for a moment, you'll see there's another possibility. It's possible that the equations have more than one solution, and that in one solution the electron has a mass and the neutrino doesn't. In the other solution, the electron doesn't have a mass and the neutrino does. The symmetry is not reflected in the individual solutions, but in the pattern of all the solutions. The universe, however, as we know it, corresponds not to the pattern of all the solutions, but to just one of them. We live in one universe in which either the electron has a mass and the neutrino doesn't, which happens to be the case, or the neutrino has a mass and the electron doesn't. In fact, the question doesn't even really arise why we live in one rather than the other, because by definition the electron is the one that has the mass. So it's not surprising. However, it makes it damned hard to find that there really is a symmetry in the underlying theory if in the laboratory you see electrons have mass and neutrinos don't. The breaking of the symmetry is also responsible for giving the mass to the electron, and in fact to the quarks and all the other particles we know. We don't, as a previous questioner pointed out correctly, we don't know the mechanism by which this symmetry is broken. We don't know why you have this multiplicity of solutions, and that is what the super collider is specifically aimed at discovering. Another question here?
Thank you. I have two questions, actually. First, I was struck by your distinction between beautiful and ugly solutions in your example of the magnetic properties of the magnetic properties of metal.
Yeah.
I wondered whether you believe that there is a beautiful solution or a beautiful explanation of the phenomena that all fermions are half-integer particles.
Oh, sure. I mean, we already have that. The fermions, there's a lot of physics in the question. Maybe not everyone in the audience knows what the question means. Half-integer spin particles are particles that have a certain spin, just in the sense that the Earth has a certain spin. They're spinning around their axis, and they spin a certain amount. And, for example, the electron has half the spin of the photon. And so we call it a particle of spin a half, because it is half the spin of the photon. Now, particles that have, like the electron, that have half the spin of the photon, have a peculiar property that they tend to avoid being in the same state. That's why all the electrons in the atoms don't all fall down to the lowest state, why they form shells, because they can't be in the same state. And that's what the questioner means when he says they're fermions. Why are particles with spin a half fermions? Well, it's because we can't combine relativity and quantum mechanics in any other way. You can show in very general terms that the combination of relativity and quantum mechanics is impossible in 3 dimensions. It is possible, actually, in 2 dimensions, but it's not possible in 3 dimensions unless this is true, that all particles that have a spin half the photon spin also have this peculiar property of avoiding being in the same state. So that's not a mystery.
I didn't think it was a mystery, but all textbooks that I've ever read stop with the basic statement you just made and say that the argument is itself highly complicated.
It's complicated only because it cannot. You've probably read a book about non-relativistic quantum mechanics, and the argument can't be made in non-relativistic quantum mechanics because it ain't true. In fact, in non-relativist quantum mechanics based on Newton's theory rather than Einstein's, you could perfectly well have any spin fermions. It's only when you combine relativity with quantum mechanics that you see that you have to have just this possibility. So you have to read a book that combines relativity with quantum mechanics.
Thank you. I was hoping your explanation was beautiful enough that you'd be able to convey it in a few minutes from the podium.
No, I can't. In
my-
fact, Emilio Segre, distinguished experimental physicist at Berkeley, once offered a bottle of champagne as a prize to anyone who could give a simple elementary explanation of that, and no one ever collected. So it's not just me.
My second question is, how does a detector that is many times bigger than a truck fit into a 10-foot wide tunnel?
Oh, no. In fact, of course it doesn't. That's a very good question. Well, no, actually, that's not a very good question. Because, there's the detector you're asking about, and in fact, it doesn't fit into the 10-foot wide tunnel. It fits into this great big hole. This thing over here is the 10-foot wide tunnel. This is an enormous thing like St. Peter's in which the detector fits, and there are only about 4 of these experimental holes around the ring. They're very expensive to excavate, as you can imagine. There's a question over there, 2 over there.
Yes. Is there any chance that Nanopolis has found the right vacuum?
Boy, these questions. What had happened? Oh, the whole physics department from the University of Oregon at Eugene came down here? I mean, really, there are people in the audience who don't know anything about what the question. In fact, in this particular case, I'm not sure I do. I mean, Nanopolis has written more papers than anyone would want to read, and I don't know the latest one. And if you want to know, I don't want to say anything. This is getting awfully ad hominem. I think I better pass on that. Let me answer one of these. Your notion of a final theory seems absolutist. How do you answer the question of description without prediction implied by chaos? I think this is terribly overblown, this business about chaos changing our view of the nature of science. Chaos is a phenomenon which is very common in nature, in which very small changes in initial conditions lead to very, very different behavior after a certain period of time. For example, if you have a solar system with just the sun and one planet, if you make a small perturbation to the planet, then you perturb the orbit in a way that remains small forever. Whereas if you have a solar system with two planets, and you make a small perturbation in their orbits, after a while, the planets are in positions which are totally different from where they would have been if you hadn't perturbed it. This was discovered, in fact, at the turn of the century by the mathematician Poincaré. However, it doesn't mean that we have a description without prediction, as your question asks. In fact, no matter how far into the future you want to predict where those planets are, there is some degree of accuracy with which you can measure their initial positions, which will allow you to make that prediction. It's not true that you lose the ability to predict. It's just in order to predict for a certain time into the future, you need more and more accuracy. And in fact, the demands on accuracy go up so much that as a practical matter, the prediction becomes impossible. Well, we always knew that prediction was impossible as a practical matter for all sorts of things. It doesn't change the fact that the planets are moving the way they do because of the laws of gravity. In fact, I would say that throughout my book and implicitly in this talk, I'm really not interested that much in what people can do as with why things are the way they are. The planets move the way they do because of the laws of gravity and the laws of motion applied to them. And it doesn't really matter that much from my point of view whether people are actually able to do the calculation. In fact, in principle, they are able to calculate where those planets will be indefinitely far into the future, chaos or no chaos. It's just the further into the future you want to make the prediction, the more accuracy you need in the initial conditions and in the way you do the calculation. So I think chaos is a big simus, and I don't think it changes anything fundamentally about the way we look at nature. Jim Glick is a good friend of mine, and he wrote a very influential book about chaos, but I still don't agree with this. Why is there anything? Is there a reason or a purpose for it? Well, of course, I was using the word why in a somewhat different sense. The philosopher Ernst Nagel listed 10 different meanings of the word why, like why did Cassius kill Caesar, and why does ice float on water? And it's clear when I use the word why, I mean something like why does ice float on water, and not why did Cassius kill Caesar. So I can't really answer. If in my sense of the word why is there anything, we may know the answer eventually. I think that was the question I was raising earlier. Is there, in the future, going to be a fusion between physics and history, as Stephen Hawking has already anticipated, which shows that not only the laws of nature govern what the universe will do once set in motion, but actually tell us that there is a universe. I don't know whether that's going to be true or not, and we just have to wait and see. The other question, is there a reason or a purpose for it? Again, it depends what kind of reason or purpose you mean. I wrote an earlier book called The First 3 Minutes, and in it I was rash enough to say the more the universe seems comprehensible, the more it seems pointless. And what I meant by that is that in studying nature, we find no point to the universe. There's nothing in our there's nothing in our knowledge of nature as it objectively is that suggests any reason or purpose or point. However, that doesn't mean that we can't give it a point. There's nothing in science that says there isn't a point. Just science doesn't suggest any point. We can give life a point by things that we invent for ourselves, our sense of beauty, loving each other, discovering the final laws of nature. And they give a point to life. But I think it is important that it's a point, it is important, something we ought to get used to thinking, that it's a point that we have made up for ourselves, which makes it nonetheless precious, but it's not a point which is, in some sense, objectively out there in the universe to be discovered. Question here?
Yeah. First thing I'd like to say is education is definitely the next best thing to discovery. And I guess chance is one of the major principles that I've discovered through my own work, and use the term natural selection. Would you attribute the same term to chance?
Well, I'm not really sure what you're getting at in your question. Natural selection certainly works in a probabilistic way. You can actually prove mathematically that if you have a population and that there are certain mutations that will make reproductive success more likely, then those genes will spread through the population. And it's all described in a probabilistic way. They're not synonymous. I would say natural selection is one application of the theory of probability. But I'm not perhaps getting to what your question really is. Yeah, another question?
Yes. Could you tell us what makes the superstring theory as eloquent as it seems to be? Why does it seem to explain so many things? What about it is so gripping that?
Well, I didn't really say very much about what superstring theory is. I said instead of point particles, we have little one-dimensional glitches in space, which can either be closed like a closed rubber band or open like a rubber band after you've cut it. And they go zipping around and they vibrate. And they're so small, they're much smaller compared to an atomic nucleus than an atomic nucleus is compared to the Earth. So they're really very small. And they look to us like point particles, but they vibrate, and their different modes of vibration look like different types of particles. That's, according to superstring theory, that's why there are all these electrons and quarks and photons and so on. They're just different modes of vibration of one fundamental entity, a string. So that's very appealing, that we don't have a lot of different types of field or particle. We just have one thing, a string, which occurs naturally in different modes of vibration, just like a tuning fork. That's attractive. The other attractive thing about it is that because they're not point particles, the problem of infinities doesn't arise. The whole problem of infinities in physics arose because we were trying to imagine things like what is the force between two electrons when they're identically on top of each other. And of course that force is infinite. The inverse square law gives you an infinite force when the distance is 0. Superstrings are not points, so they can't be on top of each other. One part of one string will always be some distance from another point of another string. And that means that in a properly formulated superstring theory, there are no infinities. That's very exciting. The third thing is that superstring theories are capable of describing gravitation, which we've never been able to do in quantum terms before because of the problem of infinities. In fact, superstring theories not only describe gravitation, they make gravity inevitable. In every superstring theory that's ever been studied, and there are unfortunately a lot of them, I mean, that's what's bad, that there are more than one. In every superstring theory that's been discovered, one of the modes of vibration of the string, when you look at it from a large distance, large compared to the size of the string, looks like a particle of 0 mass and spin twice the photon's spin. Now, those are just the properties that we know will describe a particle that would transmit gravitational forces. In fact, we know that if there is such a particle in nature, that the description of large numbers of those particles will be the same as Einstein's general theory of relativity applied to gravitational fields. In other words, superstring theories predict the existence of gravity. They not only can deal with gravity, they make gravity inevitable. And that's something that certainly no other theory ever did.
Thank you very much.
Yeah, if that doesn't sell you, I'll think of a few other things. Oh, another question there. Yeah.
Well, you'll be glad to know I'm not from the physics department, but I do read occasionally in some of these areas, including some of your work. I just wondered if you would care to comment on, I would say, the relatively recent growing acceptance, maybe even evidence, that there's may well be a lot more matter or energy
Yes,
in the
I'm glad
universe
you
than
asked
it's
that, because-
easily detected.
Yeah.
But I don't hear, which you read a great deal about, but I don't hear anything about a possibly concomitant idea that the universe might be oscillatory.
Well, yes. There is evidence, indirect but fairly convincing, that there's a lot of matter in the universe that is dark. The clusters of galaxies seem to be, the galaxies in clusters seem to be moving so rapidly that they would fly out of the clusters if the gravitational field were not strong enough to hold them in, and that gravitational field can't be accounted for by the visible light that we see in galaxies, and it seems that there's a lot of material out there which is just not visible as light. Now, in fact, in modern cosmological theories, the most popular theories require even more matter than that, so much matter that you would get into contradictions with the production of the light elements unless it was a new kind of matter that didn't interfere with those nuclear reactions in the first 3 minutes. And so we think it's likely that there's some kind of exotic particle that hasn't been discovered yet that makes up most of the matter of the universe. And this is the missing matter or the dark matter. One of the things that's most exciting about the super collider is that it has a chance, although we can't speak with any confidence, of discovering this particle. And there are various ideas on how to do this, so that the super collider may, I have to say may not, identify the particle which makes up most of the mass of the universe. Now, if there's a lot of this stuff, even more than is called for in the most popular modern cosmologies, then eventually the expansion of the universe will stop and the universe will recollapse into a point singularity. And then the question is, what happens then? And that's where the possibility that maybe the universe oscillates comes in. Maybe the present expansion of the universe is just one phase, and that the universe actually goes through an alternating cycle of expansion and contraction. We know of nothing, however, that could reverse the contraction of the universe once it starts. And so there's no physical theory that would explain an oscillating universe. And also I think there's indirect evidence that we don't have an infinitely old oscillating universe, because then it would be infinitely hot, because in each cycle you produce a little bit more heat. And so I'm a little skeptical about the idea of an oscillating universe, but it's certainly one that has been on physicists' minds for a long time. There was questions over there which I haven't gotten to in a long time, because I can't see you over there.
Okay.
Yeah.
Do you consider consciousness an entity? How would you relate it to your comments about laws of nature? And what relation would it have to a super collider?
Well, the last part of that question is easy. I think consciousness is certainly one of the things that's not likely to be illuminated by the discoveries made at the super collider, or indeed by the discovery of final laws of nature at all. Consciousness is, in a way, is the most mysterious thing in nature, because we know more about it than we know about anything else. We know about consciousness directly without the intervention of the senses. And therefore, it's hard to study it, because in studying anything, we use our senses to studying it. But consciousness is something we know about without the senses. We just feel conscious. Some physicists, like Brian Pippard, have said that we will never understand consciousness in a reductionist way in terms of fundamental laws of physics. He may be right. I don't think so. My guess is that we will be able to understand consciousness in the same way we understand everything else, and that when we understand behavior of organisms, from worms up to people, eventually we'll recognize in the program that produces that behavior something analogous to our experience of consciousness, and we'll say, well, that's what corresponds to consciousness. You know, nervous systems are very complicated. We don't really understand them, but they're not infinitely complicated. There's a small worm called C. elegans whose nervous system has been completely mapped. Everything about the nervous system of that worm is now known. We don't know the program that is programmed into that nervous system that makes the worm behave the way it does, but we probably will learn that in the foreseeable future. And so we'll be able to say we understand everything about why the worm behaves the way it does. That's a very simple organism, and it's not remotely as complicated as a human being, but I don't see any insuperable gap between worms and people. You know, there is a continuum from worms to insects to fishes to mice to monkeys to people, and along that continuum I don't see any absolute sharp barrier. Perhaps the one discontinuity is language. I mean, the one thing that seems to me really qualitatively different between people and everything else is that we can speak, and maybe consciousness is just that. Maybe it's just a conversation we carry on with ourselves, an unvoiced conversation. And maybe there would be no consciousness without language. I don't know. I admit in my book that I find this question very difficult, and that's one of the few things I admit that about. Yeah, there's a few more there.
Yes?
Yeah, I think what I'm going to do is just take everyone who's on their feet now and then call it a day, a night.
Yes?
Please go ahead.
When these protons are crashing together, are the patterns going to tell us anything about what happened to all the antimatter?
Oh, I don't know. I mean, the universe is asymmetrical between matter and antimatter, at least it seems so. As far as we can tell, there's not much antimatter in the universe. It's all matter. We believe, actually, that that's slightly misleading, because if we go back to before the first 3 minutes, in fact, to about the first 100th of a second, at that point in the history of the universe, there was almost equal amounts of matter and antimatter, perhaps one extra particle for every billion pairs of particles and antiparticles. In other words, the excess of matter over antimatter in the very early universe was about 1 part in a billion. And what happened after that was that all the matter annihilated antimatter wherever it could, leaving over just that tiny residue of matter that couldn't find any antimatter to annihilate with. And that's us, and the stars and the Earth and so on. But in other words, the discrepancy between matter and antimatter in the universe is actually very small from that point of view. It was very small historically, and it only seems large now. Where did that very small discrepancy come from? Well, the Soviet physicist Sakharov suggested, he was the first person who regarded this as a real question for theoretical physics, and actually suggested ways that that discrepancy could come about. The key thing, there was a certain symmetry that has to be violated. Obviously, it's a symmetry between matter and antimatter. What else would it be? That has to be violated in order for that discrepancy to arise. And we're just beginning to learn the way that that symmetry is, in fact, violated in nature. And the super collider, to finally come to answer your question, in fact, would be very helpful in answering the question of how that symmetry is violated. My friends from Eugene will probably recognize that symmetry is called CP symmetry. And this is one of the mysteries about the Standard Model. We don't know what is the mechanism by which this symmetry is violated. And the super collider will, in fact, help us to answer that question. And in fact, it very likely has to do with this mysterious thing about the mechanism by which the other symmetries of the Standard Model are hidden. So the answer is yes, it's very possible the super collider may help us to understand why there's an imbalance between matter and antimatter in the universe. Question here?
Yes. To the best of my knowledge, negative energies have never been detected in nature, yet negative energies are used throughout theoretical physics. How do you account for that?
Well, it's almost a principle we take as an axiom that there is a state of lowest energy, which we call the vacuum, and that anything else has to have a higher energy, which by convention is a positive energy. Unfortunately, one of the things that's wrong with present superstring theories is that they don't agree with that they have solutions with negative energy, which don't correspond to anything we see in nature. In other words, by negative, I don't just mean a minus sign, because that's partly a matter of convention. I mean less than the energy of empty space. That's disturbing, because then why is empty space not unstable? And it isn't. You can watch empty space for a long time, nothing happens. So this is one of the problems with superstring theories, is that they tend to have solutions with negative energy, and that's clearly contradictory to observation. I don't know what more I can say. Yes, another question?
I guess this is the last question.
Yeah, good.
What do you think of David Bohm's ideas about the implicate and explicate order, the wholeness, his ideas of wholeness and connectedness?
I haven't studied them, I'm afraid. He just died, and de mortuis nihil nisi bonum, but it's odd that quantum mechanics, as I said, was developed in the 1920s. It is the basis of everything we do in physics. The latest, most fashionable, most esoteric superstring theories are still formulated in terms of the same old quantum mechanics that was developed in 1925-26. And in fact, we think that quantum mechanics probably will be part of the final theory in its present form. Sometimes people say there's no physical theory that will survive indefinitely into the future. I think quantum mechanics very likely will. Quantum mechanics has terrible problems of interpretation. We had a question earlier about Bell's work. It's very hard to understand in quantum mechanical terms what one is doing when one makes a measurement. And there are people like David Bohm who've given their lives to working on those problems. And I respect that work, but I regard it as one of the odd things, the reason for which I don't know, that none of that work has ever had the slightest effect on the progress of physics. In other words, quantum mechanics is something that we seem to be able to use perfectly well without understanding on the deep level that David Bohm wants to understand it. I tell a story in my book about standing waiting for an elevator in Austin with a colleague, Phil Candelas, who's in my department, and we were talking about a graduate student who had seemed very promising and then had dropped out of sight. And I asked Phil what had happened to this graduate student. He seemed so promising. And Phil shook his head sadly and said he tried to understand quantum mechanics. Thank you.